Hello everyone. We are really happy to see you here on the second live stream of the series, How to Build AI Agents in Kotlin with Koog. My name is Vadim, and my usual co-host is Andrei. Actually, this time he will be showing much more of the code rather than me. Today we're going to talk how to build your agents and make them smarter. So compared to like the previous live stream, and I really recommend watching the first series before watching this one to get the understanding of the basics with Koog. And during this session, we will be making your agents more predictable. Also, we will be interacting with external tools via MCP. Is that correct, Andrei?
Yeah, that's right. I prepared some nice MCP integration with Google Maps.
Yeah, perfect. And also we will talk a little bit about the observability and tracing, but just a little bit about that, because we're going to have a separate session of a live stream or maybe a separate video about the observability. So this time more of a basic stuff about that. And finally, like the goal of this live stream is building a trip planning agent, right?
Yeah, that's right. I guess I can tell a bit more about the agent that we're going to build today. And yeah, let me share my screen and I'll walk you through the idea, basically what we are going to do.
Yeah, sure. Thanks, Andrei. Please feel free to share your screen. I would also like add up here that please feel free to ask any questions. I'll be watching you like through the chat, and this session, unlike the previous one, will be more of a relaxed session with like very much free format. So Andrei will be live coding. I will be making some comments, and you're always free to ask any questions. If you don't understand or don't like something, please feel free to tell your opinion in the chat. So here we go. Andrei, please.
Yep. So let's take a closer look at the idea. As Vadim already said, we're going to build a trip planning agent. And here I created a overview, like high-level overview graph of the strategy of our agent. So basically, what's the idea? The idea is that there's a user, and user asks our agent, like, hello, I'm going on the vacation to a certain location for certain dates. Help me plan the vacation, basically. Suggest me a list of places to go to, of some sites and experiences to visit. And that's what our agent is going to do. So the strategy, the high-level strategy, again, I didn't specify all the building blocks. We will be taking a closer look at this in the code. But the high-level strategy is we get initial message from the user, and there is a first step. So first, we want to clarify some things that are not clear from the initial user message. For example, we need to make sure that all the dates, all the places, and all the user preferences are clearly understood by the agent, and we get a full user request with a full plan. After this initial clarification step, we go into the sort of main stage, sort of central idea of our agent. We are going to use Google Maps tools through the MCP server and also integrating with the external weather forecast API to use all those tools and use a loop to think about possible suggestions, and then provide a draft plan to the user. Like here, for example, I see you're going to this location. Here are some places, here are some spots you can visit, and then we're going to pass this plan suggestion to the next stage to ask for the feedback from the user. So this is our suggestion. Do you like it or not? And the user would be able to either accept the final plan, and this is the ideal scenario, but most likely you, like as a user, you would like to correct something because there are certain things you forgot to mention, or there's something wrong with the plan, or just, yeah, you just want to add something. So in this case, we would be able to provide a feedback just as a message, and the agent will like repeat the previous action, the previous stage. It would reconsider, like take our feedback into account, and basically do the same thing with the thinking, using Google Maps, using weather forecast, and so on, and provide us the next plan suggestion. And it will be doing this until the user, or the user, us, will be satisfied with the final plan, and until we accept the final plan. So this is the high-level overview of the strategy. And I guess we should go straight to the code and take a look at what this agent actually does, how it's implemented, and how to integrate all those tools into our agent.
Sorry, Andre, could you please like go back to your strategy before we dive into the coding part? Because like I'm pretty sure like some of the viewers might have this question, like why do we need this like complex graph with all that domain specific things in the strategy compared to just like the simple agent that everyone pretty much already knows from the previous session? Like you can just throw the bunch of tools to the LLM, write it in a very good prompt, and then hope that it's going to work.
Yeah, that's a great question, and it actually touches on the very important topic of limitations when working with LLMs. So of course, you can do this. You can just use a simple strategy and throw all the tools, but then you will have some troubles controlling the behavior of the agent, because LLMs are not magical, and the more information you give to the LLM, the more confused it becomes. So building custom strategies allows you to sort of like guide the LLM to the correct solution. It saves us time, it saves us money because we spend less tokens, and our users will be more happy because they get more accurate responses. So building custom strategies allows us to precisely control what we want from the agent. I hope that's clear. And yeah, if there are any other questions, if there are no questions, we can go to the code.
Yeah, thanks, Andre. So that's exactly it. So instead of like building this like random guesser machines and hoping that it's going to work, we can basically never do so, because like even if it's working like with a rate of 95%, if you deploy it to like the real production environment, 95% means it's not working always for your users, meaning that eventually some users will be always getting upset. So instead of like hoping for the best future, it's much more robust to provide this like precise strategy that you can program and make it working always to the extent of basically how well it's programmed. So instead of hoping for the LLM, you'll have to basically hope for yourself as a developer. So as good you can program this strategy, this will basically reflect how well the agent will behave in the real life. So basically, the limit is not the LLM. The limit is like yourself, right?
Yeah, that's a nice way to put it. Yeah, I like it. I like your analogy. So yeah, I guess we can finally see the code, right?
Yeah, sure.
So let me explain some stuff step by step, and then we'll take a closer look at the strategy part that is actually the most interesting for us probably today. Yeah, first of all, about the integrations. As I mentioned, we're integrating with two external services here, Weather API and Google Maps API. And to integrate with Weather API, there's actually a nice and most importantly free public Weather API. It's called OpenMeteo. It does not require any API keys whatsoever. You're free to call the API endpoint and get your results. So here we have a simple API client that is just it's really simple. We have again, I'm using Cater because we're using Kotlin, and we want to get this nice suspend everywhere and so on. So I'm just using Cater to support two API functions. The first one is the one to search for location. to do to get the precise coordinates as a response. And yeah, as you can see here, it's just again simple REST request and getting some response back, and the weather forecast function that does something similar. We're just providing a number of parameters like the coordinates of the desired location that we want to check weather forecast for, the start date, the end date, and yeah, number of other parameters. And again, just doing some simple HTTP request and getting the response back. So really, that's just the whole weather API. And here we have some structures that we will be getting as a response. Nothing too complex here, and I won't be focusing here too much because it's just a familiar API integration. What's more interesting probably is how we can use MCP, how we can use Koog to integrate with MCP, because MCPs are cool. They essentially allow you to get tools for free. So as you can see here, I had to code my API integration by hand, but with MCPs, it's already there. You can use it. And with Koog, there is a already present integration here. So what you need to do, we're using Google Maps Docker server with MCP. So you just run this Docker image with MCP, wait for some time until it started. There's probably a nicer solution. You can implement some fail-safe way to wait, but I'm just using delay here because it's we're not building a production app here, right? So it's fine. And then we get a transport as a response back after configuring all this stuff. And yeah, let me uncomment this part. And so, yeah, as simple as that, we can get, we're getting like, actually, let me go here. We're getting our tool registry. Sorry. Yeah. So we just need to perform two steps. First, we need to instantiate the transport, basically a connection to our MCP server. In this case, as you can see, I'm interacting with my MCP using stdio. And then after we configure this connection, we can just pass it to the factory function to get the tool registry. And the concept of tool registry should already be familiar to you from the previous live stream. So tool registry, the collection of tools that we get to that the model can use to interact with the environment. So this is probably the more interesting part, and I guess we can try some live coding and just to see what's inside this tool registry, right? So let me comment what's already present here. And we'll just, I'm commenting out the logic, like the actual agent logic that was here, because right now we just want to just take a look at what's inside. So I can, first I need to get my tool registry, and I can just copy this part. I can just copy this part here. And for example, we can do this. We can print all the tools that are available here. And maybe we don't want to print the tool. Maybe we want to print tool name. Yeah, and let's run this. So this is
Andrei, sorry for interruption. There is a question in the chat about the Google Maps and the Docker. So the question is, there is a Docker for Google Maps. I guess that provides the MCP server itself, right?
Yeah. So this is not the official Google supported MCP server. It's like a sort of simplified. This MCP server does not expose all the API endpoints available through Google Maps API. It's just like some simplified MCP server developed by the MCP Foundation, I guess. And yeah, it's it's available on Docker Hub. You can use it, you can download it, you can play with it. And since we're building like a demo agent, we don't need all the tools. Actually, it provides a number of useful tools already, and we can see it if I'm going to run this code, and we can actually see what tools are inside, and we can see that for our agent, this should be enough already. So yeah.
Yeah, thanks, Andrei. Maybe let's also like comment about the basically types of MCP servers that exist. So basically, there is a Docker MCP, which means that your application will communicate with the MCP server via the like std in, std out. And another type is the REST API MCP server, right?
Yeah, that's right. Only it's not REST API. It's like SSE, server-side events, using JSON RPC protocol. But again, you don't have to concern you with all the details, because with Koog, you can, for example, if you don't want to communicate with your MCP server using STDO, you can always use default SSE transport, and then just provide the URL. Like suppose your MCP server is hosted somewhere like locally, you can always do something like this, for example. And so just you need to change only one line of code to use a different transport. And as you can see, I ran this code. So just starting my MCP server and printing the list of all the tools that are inside. And as you can see, there's like not many, but a number of useful tools. For example, search places or geocode. That's not much, but it's probably all we need. So and since this is a regular tool registry instance, as you can see, you can play with it. You can, for example, you can not only print the name of the tool, you can also, I don't know, you can print println not description, but descriptor, and tool description, and for example, to get more information about those tools. So we can see like not only tool names here right now, but also descriptions of those tools. And all of this, it's not hard-coded anywhere in the code. It's just coming from the MCP server itself. So all we did was just configure the connection to our MCP server, and then use this connection to get tool registry from here. That's all. I guess this should be more or less clear about the MCP part. If you have like more questions, you can always check the examples on the Koog repo and check the documentation. And Vadim, do you have any comments here? Maybe you want me to do something more, or we can just move on to the next part.
Yeah, I think for now it's fine. Let's just move on to the next part.
Yep, perfect. Let me just remove this part because we don't need it. And so we covered weather API integration. We covered MCP integration. Let's probably talk a bit more about other tools that we will be using here. So this quite simple tool, but it's kind of important here, is add date. And why do we need this tool? So as we all probably already know, LLMs are basically predictors. They don't calculate anything without any specific tools. They just predict the next token. So if we need to do any calculations, it's better to provide appropriate tools to do so for the LLM. So for example, since we're working with dates here, and since we're working with user requests, it's highly likely that the user can say just, oh, I'm going on a vacation in 2 weeks. And then LLM needs a way to somehow calculate when those 2 weeks are going to be basically in the future, because it needs those dates to check weather and so on and so forth. So This is the tool. Basically, it's using the familiar syntax from the previous live stream. It's just a function annotated with the tool annotation. It has an LLM description with the tool description, some parameters, and it just appends, like, sorry, not appends, but it adds days and month to the past date and returns it as a string. Nothing too complicated. And probably more interesting tools are user tools. It's a bit more complicated way to define our tools because it's not a standalone function. It uses a thing called toolset. Again, it should be familiar from the previous live stream. So what this toolset does, it's a way for us to group related tools together. And it's also a nice way to inject some external dependencies for our tools. So, for example, yeah, here we have our user tools that are the tools needed for user interaction, basically, because we need to show the message to the user. We need a way to interact with the user. And for that, we need some external dependency. Here is just a lambda really simple lambda that takes the message to show as a parameter and returns user response. So just string to string. And the tool that just calls this lambda. Yeah, we just call this show user message, and we're doing something. Again, should be pretty straightforward, especially if you watch the previous stream. And yeah, a bit more complicated tool is weather tools. Again, it's a tool set. It's a tool set because we want to inject external dependency. In this case, we're injecting the weather API client. And here, what we want to do here, we want to transform the response from the API as it is, because it contains lots of parameters in some format that is not necessarily good, like in a nice format, in the appropriate format for the LLM. So we want to transform the raw response from the API client to something digestible by the LLM, something that LLM would understand. So here we're just doing some, like a bunch of transformations, really. We take some arguments as a tool argument. So we expect the LLM to provide us a location, country code, start date, end date, and the desired granularity, so hourly or daily. And then again, it's mostly just some data transformations, so I won't be diving too deep here. It's just a bunch of classes that we need to represent the data, and the probably more interesting part is the final representation of this data, how the LLM would see the forecast. So here we have this toString method on the forecast, or sorry, probably on the result, on the result class. And yeah, we just handle different states of the result. If there is an error, we just provide an error text to the LLM. If the location is not found, we say that location is not found. And if there's no forecast, we say that there's no forecast available. And then we use a Markdown utility builder. It's also coming from Koog because we support several popular text formats such as Markdown or XML to format our response so that the LLM would understand it better. And here we just process the response. So basically building some Markdown text with all the dates, with all the weather descriptions, and with all the data from the weather API. And yeah, we can, again, since those are just regular functions, regular classes, we can always just play with it manually, and we can do this. I suggest you to do this right now to see what's actually inside. Yeah, Vadim, you want to say something?
Yeah. Sorry, Andrei, for the interruption. I would just probably ask a question. Like, could you please go back a little bit to
To the
the
weather
function?
tools, right?
Yes, right. So here, as everyone can see, like there is a toString override for the final class of the result, and the function itself, like the tool that will be available to the LLM, returns string. So in the previous live stream, I think, like we saw that basically any function that returns any serializable result, which is again serializable, that's very important, can be transformed automatically to a tool. But why do we need to like explain it with a plain text? Why do we provide this string output to the LLM instead of just providing the result and then hoping that LLM will understand it better?
Yeah, that's a good question. And the reason is that we want to precisely control the format of the output, because the raw weather forecast response would probably be too verbose for the LLM. For example, yeah, we can see actually the structs that are returned as a response. And here, for example, you see like daily forecast, what it contains. There's like some weather code. Again, no idea for the LLM what this weather code actually means. So we are mapping it to the clear string description. And then a bunch of lists, which are not really, I mean, if I read it without reading API specification first, I wouldn't probably understand a thing here. So to increase the accuracy of our responses, to increase the accuracy of our agent, we need to transform the response to something that is basically a human readable text, something that can be understood just by looking at it. And so we're doing it here because we have like a sealed interface forecast, because we have two types of forecast. We have a daily forecast, we have an hourly forecast, and each type of forecast has a list of data points with, for example, the date, weather description, and some parameters like temperature and precipitation. And then we can use and of course the final result structure that we will be transforming to the string output. And so we essentially, this tool is just a transformation layer between the raw API response and the nicely formatted string response. That's what this tool does basically. Yeah, and here we're just transforming it to the string.
Yeah, thanks, Andrei, and thanks for basically looking through all the data classes. So yeah, like from my side, I would probably add up that it's like very important to think about the LLM as you think of like your friend who doesn't know programming. So like you have to explain everything that is happening with like one more important thing. Like basically, if you talk to your friend, the only thing that you spend is your time explaining the meaning of something. But for the LLM, you also pay your money. And for example, another important thing is like basically when exception is happening, one of the common mistakes is like you would just give the whole exception stack trace as a string to the LLM, but you will have to basically pay your money for all that text, for all that tokens that you spent for the LLM, like reading the stack trace and also figuring out what's happening there. So instead of this, it's like one of like very important patterns to provide the minimal required but sufficient information to the model so that it can figure out like what's happening there.
Yeah, and I also see questions in the chat about the repo. So yeah, right now this code is not available anywhere, but after the stream, just as for the previous stream, I'll upload this whole project to our examples module in the main Koog repo, so you will be able to check it for yourself, to play with it, and so on. Yeah. And yeah, shall we take a look at how the weather tools actually work, just to see what the LLM would get as a response? And yeah, we can take like weather tools open Meteor client, and we can, again, it's just a simple function, so we can call it directly. And I even see some suggestion from the AI assistant. Basically, it suggests me to check the weather in Paris between 20th and 21st of May. But that's not what I want. That's too far in the past. So let's maybe check like August, like 25, and then like 2025, 8/27, and forecast granularity daily. And here we get basically a string as a result, and we can print it. We can print it to see what the response actually looks like. Yeah. So as we can see, we called the tool with those parameters, and we get nicely formatted markdown string as an output, like daily forecast for this location, Paris, France, with all the dates, with the text description of the weather condition, and yeah, and we can also do this like if we take hourly. Here we can see more detailed forecast for each hour. Yeah, so basically the same, but now for each hour. So yeah, pretty straightforward tool, just getting a nice string forecast. Yeah, shall we move on to the agent itself?
Yeah, let's do that.
Yeah, let me remove this code here because we don't need it. So let's take a look at the agent implementation, actually. So here, how the agent implementation might look like. For example, we mentioned the simple agent that you can, of course, implement your agent as a simple agent. And let's take a quick look at how it could potentially be implemented. So we're just taking a bunch of external dependencies, like a prompt executor to run our LLM requests, the Open Meteor client, tool registry with Google Maps tools, and some event handlers to interact with the external environment. And yeah, to implement this simple agent, we just need to create a number of tool sets that we're going to use here. And then we just create a tool registry. And by the way, you can create multiple tool registries and combine them with the plus operator. So for example, here, since we're having like an external tool registry that is Google Maps MCP, we can combine our tools with the MCP tools, and we will get in like again a tool registry, a final tool registry as a result with all the tools combined. Yeah, and a simple agent is just that. We're not passing any strategy explicitly here because we're using a default one. We're just providing a system prompt, number of parameters like temperature and LLM model, and yeah, just asking it to use all the tools at your disposal. Give me a plan suggestion. So yeah, that's a simple agent. That's a simple agent. I'm not going to run it here to save us some time, but yeah, probably if you would run it, you will get like it might work, and it will work, I would say, but the results might be unstable. It might take a long time, and so on and so forth. Basically, all the problems with the simple strategy as I explained initially. So let's just hide it here now. I guess, yeah, like this. And let's take a look at our actual agent that we're going to run today. So the dependencies are essentially the same because we also need a prompt executor, we also need a client, we also need a like a weather client, we also need a tool registry from our MCP and external like handlers. Yeah, let me probably cover the main also first, just so that you have an idea how this agent is interacted from the user perspective, and then we will go deep into the agent implementation itself. Okay. So from the user perspective, like from the someone who integrates this agent into the application. What we have to do, just like this. So again, those are my external environment variables. I'm reading some API keys from them. Then I create the transport connection to the MCP server. And then I create my planner agent. I'm using multi-LLM prompt executor. So basically what prompt executor does, it's sort of an abstraction of the Koog framework. That is, I can just download the sources, and we can check the, go back really quick. We can check the interface itself. So the base interface of the prompt executor, it's quite simple. It's got only like 3 or 4 methods, and it provides a high-level abstraction over executing the prompt. This is the most interesting part. It just says like, okay, given a given prompt, LLM model, and a list of tools, what are the next messages? And so using this like high-level abstraction, we can create in some advanced use cases, you can create your own prompt executors, but we're not doing this here because, again, Koog provides nice sane default presets. So with Koog, there is a single prompt executor, which you probably already seen. It's what is created. For example, if I want to interact only with one LLM provider, for example, OpenAI, I can do prompt OpenAI prompt executor and use prompt executor and use simple OpenAI executor. And then here goes my OpenAI key. So that's probably you're again already familiar with. But in my case, I want to be able to switch to different models, to different LLM providers. So it's a bit more advanced, but again, should be quite straightforward. I just define multi-LLM prompt executor and then define the mapping. For example, for OpenAI, I'll be using OpenAI LLM client with this key. For Anthropic, I'll be using Anthropic, and for the Google, the same.
Yeah, Andrei, so there is a question in the chat that I would like to highlight right away.
Okay.
Just by the way, I am saving some questions for the end of the stream that we will be answering during the Q&A. So if you feel that your question is unanswered, we might answer it there. But like this one looks like very much related to what's happening on the screen. So the question is that multi-LLM prompt executor, if it has OpenAI, Anthropic, Google as the example, how does it decide which one?
Yeah, really good question. Thanks for asking it. So if you take a look at the model definitions that we provide, for example, OpenAI models, chat, and for example, GPT-4o, every LLM model instance has a provider field because every LLM model has a certain provider. And that's what actually matters here, because when we run our prompt, I showed you previously, I can show just the implementation here. It should be quite straightforward. We're just using given map of all the LLM providers and LLM client, and when user asks, for example, to execute this prompt with OpenAI GPT-4o model, we just take a look at the LLM provider of the model and get the correct client from the mappings and use it. So as simple as that. Just define the correct LLM providers here for your models.
Yeah, another important thing is that basically at the very beginning of any agent, whether it's a simple agent or non-simple agent, you always provide the initial model to start from. Then another important thing is that inside your strategy, you have a way to change a model anytime in any node, or even from inside a subgraph. I think Andrei will show it today. So that's Koog takes care of like switching the model underlying to the prompt. And by the way, like, could you please open up again the prompt executor interface, the basic execute method, which has prompt and model?
Yeah, sure.
Yeah, like this execute method. So basically the prompt here, if you navigate to the prompt, it's not a single method. So prompt is not one method, sorry, not one message. Prompt is a list of messages. It's like the whole history that is currently saved by the framework under the hood. So it's like the currently achieved state of the agent, including all user and assistant communications, including all the tool calls and tool responses. All of that is like a prompt. And then the framework takes care of like switching to another model if it's like strictly programmed in a strategy, and it transforms all the formats of tool calls and everything else for the next model so that it can continue right from there with saving the whole history before. So that's the power of that approach, and that happens automatically under the hood. And another cool part is that in the very nearest future, we are planning to also support the automated switch between models so that you can select, instead of saying like, please use GPT-4o, you would be able to say like, please use the cheapest model available or the fastest model available. Yeah, sorry for interrupting. I think that was like an important.
No problem.
So yeah,
that's the important part.
Let's probably like move to the strategy part.
Yeah, sure. Yeah, absolutely. So again, our create planner agent function, the setup is previous as before, just defining some parameters. And the the most important part here is our custom strategy. So our custom strategy, we have support for in the Koog framework. We have support for custom input and custom output types. So that's why I'm using some user input data class here as an input. It's basically the message from the user, some additional parameters like current date and the user time zone. And as an output of this strategy, I'd like to get a class, a tree plan class with all the steps and with all the suggestions. So just using the power of the custom inputs and outputs to get not just a string, but the typed class as an output. Yeah, and now I can probably show once more the picture, the strategy that we want to build, and let's go step by step and take a look how each step is implemented here. So the first step here is we want to clarify dates, places, and user preferences. But actually, step number 0 that we want to do, we want to augment our default system prompt, because there is a global system prompt that is sort of constant, that is defined once in the configurations and we want to use. But then we also want to append a certain additional information to our system prompt for each run, not for like the whole agent, but for each run. We want to append a certain additional information. And in this case, we're appending today's date, so that the agent would understand when the user says like, I'm going on the vacation in 2 days, like which date to take as a baseline to add those 2 days to. So here's like a custom node, and we're defining it by using the delegation capability of Kotlin, and then using a node function. It takes an input type, what is the input of this node, and the output type. So the input is our user input, because this will be the first node after the node start in the graph. So it takes user input and produces a string. This is the next message for the LLM with the actual request from the user. So here we are using the LLM property from the AI agent context, because as was mentioned during the previous stream, inside this lambda function, that defines the node behavior. We have take a look at this. We see that this is the context. So each node has access to the agent context, and this context provides us with a number of useful parameters. So for example, we can check the agent ID, we can check the initial agent input, and probably the most important property here is LLM, because it allows us to actually interact with LLMs. And so I'm using this LLM property here, and I'm acquiring a write session, because there are two types of session. There is a read session, and there is a write session, and it's essentially a read-write log, because as prompt is a list of messages, and we can also change a number of parameters in during the agent execution, like the list of tools. We want to make sure that our code is concurrent safe. So if we make any write changes to the agent, such as updating the prompt, we should acquire a write log. So we're doing write session, update prompt, and this is all DSL that is coming from Koog, and that allows us to perform various operations on the agent, on the prompt, with the tools, etc. And we return, as a result of this node, the user message, the original message from the user. Yeah.
Andrei, let me interrupt you here, because there is a question in the chat which is very much related. So the question is the history shared within the entire graph? And yes, the answer is yes. The history is always shared within the entire graph, but you can basically modify how you will change the history. I think in the future, Andrei will show some more precise ways of doing so, but update prompt is one of the examples. So when you call update prompt, you're not updating the prompt like in the terms like of changing the prompt. Update prompt just appends the new methods under the history. So basically, it's like if you are thinking of the ChatGPT window in front of you, update prompt just dumps a new message at the bottom. And here, Andrei dumps a system message at the bottom after basically another system message. But you can also add up like a few other messages under that. Like you can also write user message, assistant message, and so on in the same Lambda, in the same update prompt closure. And basically all other methods, all other nodes like call LLM, what they do is basically they interact with LLM or with a tool, and they also update the prompt using a similar method. So that's what's happening. And basically the history lives with you throughout the whole graph. But then there are like tricks how to change that and update the history to something new. And I think Andrei will show it later.
Yeah, and I'll also see a question about truncating the history in the chat, and I'll also show a bit later, because we're actually truncating the history in this strategy to save us tokens. But yeah, anyways, so this is the initial node, the manual node that we defined. Yeah, then the next step after we got our initial message and transformed the system prompt is to clarify the plan. And here we're using a quite powerful component from the Koog library. It's called subgraph with task. So basically, we figured out that a lot of workflows can be broken down to a subset of sequential steps, and each step is a tool calling loop with a limited number of tools that are relevant only for the given task, and some, textual definition of the task here. And with Koog, there's already a library function. It's called subgraph with task, and it has multiple overloads. You can check the docs, you can check the kdocs, and basically you can just subgraph with task type the name and see the auto-completion here. But they're all pretty much the same. The only difference is some convenient overloads with some convenient parameters. But the idea of subgraph with task is the same. We're just providing an LLM with a limited subset of tools. so that it won't get distracted by all the tools available. Only some of them are here. And then given some instructions, given some request to the LLM, what it should achieve here. So this is just a node. This will be just a node. It's a subgraph, but each subgraph is actually a node. So you can pass a string input here in this node, and then you will get a trip plan class as an output from this node. And the lambda here that defines the task, it accepts like the input that we provided to this node, and then we need to, as a result, in this lambda, we need to return a string definition, like a string request for the task. And here, I'm using, again, another text builder from the Koog. This time I'm using XML because LLMs are actually quite good at understanding XML. It's a structured data, so it's a nice way to sort of structure long prompts, long messages to increase the quality. So here I take the user message and I put some instructions tag with instructions for the LLM, like clarify user plan, to clarify all the information. And then in another tag, I append actual message from the user. So this is the concept of a subgraph. I guess it can be a little bit complicated maybe at first. And if you have like any questions, I can elaborate. But it's basically, again, I can repeat it just to make things clear. So what subgraph provides you? It provides you with a pre-built component to perform a certain task with a certain limited set of tools that are relevant only for this task, and to get a result, a desired result, a string or a structured data like a class as an output. So actually, lots of workflows can be broken down as just a number of subgraphs that are connected with each other. Yeah, I hope it's more or less clear. And we will see subgraphs in action when we run the agent.
Yeah, let me also probably add up here that basically subgraph with task is essentially a simple agent, or the default out-of-the-box agent, that has a few like tweaks here and there that basically manipulate the tools, rewrite the history so that it works and doesn't break if you provide less tools than were available before to the LLM. You can also like switch the model, and you can also force the LLM to call one specific tool at the end if it's sure that the task is done. So it's essentially another like loop with a tool calling in order to solve your task. And basically the beauty of this compared to just spawning another independent agent outside of your graph is basically that you can share the history. You can share the whole history of conversation and tool calling and pass it to this subgraph, or you can think of it as sub-agent that basically will not start from scratch, but it will start from the whole history that was behind. And Koog takes care of like rewriting this history correctly so that the new subgraph will work with it correctly. So that's basically the idea of it.
Yeah, exactly. And so actually those two steps in our high-level strategy are represented as subgraph with tasks. So this is like the first step. It's more simple. We just ask to clarify the user plan. And yeah, and the second step, the actual like suggestion part, it's as you can see, the prompt here, it's like more verbose. We're giving more information to the agent here. But the idea, again, it's similar. We're getting some suggest plan request here. I'll explain a bit later why it's not like a user plan or just a string. And we're getting a trip plan suggestions from the agent as a response. And again, just doing a similar approach here, providing a list of tools. So in the first subgraph, we provide user tools. In this case, it's like only show message tool that interacts with the user, and add date tool that just a date tool we already saw it here. It's just a function that adds the date. Because that's all the agent needs at this stage. And this jest plan step, it takes Google Maps tools and weather tools, just as I wrote here in the graph. We need to use those external integrations to provide the plan. And then the prompt, it's quite long, basically trying to combine the power of structured XML and structured Markdown to explain to our agent what it has to achieve, what is needed from the agent, what are some guidelines regarding the tool usage. So it's pretty long, but trying to be as explicit as possible here. And why do we need like some custom class here? Well, that's because if you take a look at the graph, there are actually two connections. The first, the initial one, when it's the first time the suggest stage runs, and there is like a second path, the second connection here. It's all the subsequent times the suggest stage runs. And at this stage, we have more inputs because there's not only a user, like initial user plan, there is also a user feedback that we need to take into account. And there's also a previous plan suggestion that was generated on the previous step, because we want to show this previous plan suggestion to the model so that it can improve on this. And yeah, that's why there's this idea is represented as a sealed interface hierarchy in the code. There's like a suggest plan request structure with two implementations: initial request that contains only the user plan, and the correction request that contains not only the user plan, but also user feedback and the previously suggested plan. Yeah. And so that's why, since this task definition prompt, it's a Lambda, we can write some code here. We can use the DSL. So we are using the when statement to define exactly what we want. The initial prompt, like there is a common part in the prompt that just like some common instructions, and then we are using just plain Kotlin code to tell, like, if it's initial request, then we just append the user plan. And if it's correction request, we also want to say the agent, like, user asked for corrections, please provide updated plan, and provide not only the user plan, but also previously suggested trip plan and the user feedback message. Yeah, but again, it's just a subgraph under the hood. So just a tool calling loop that tries to achieve a given goal defined in this Lambda. Yeah, and that's pretty much the important parts of the strategy. Yeah, and about the Markdown thing, that's a great question, because we realized when building Koog that there are certain textual formats that are used commonly when working with LLMs. So yeah, this Markdown part and also the XML part, it's coming from Koog. So you can build XML, you can build Markdown. Yeah.
Yeah, one of the reasons for that is basically when we were working on our agents inside JetBrains, and we were like evaluating them on different benchmarks, we realized that because of the fact that LLMs were trained on a lot of the data from the internet, and all of this data is usually structured, which is like either Markdown, HTML, XML. LLMs understand these structured prompts and structured intermediate results from the tools, for example, much better compared to unstructured text. And that is the reason why we added this DSL to Koog, so that it's much like easier to build these structured things. And then like, because it's a DSL, you can compose and remove and reuse it in many different places.
Yeah, and I want to cover some like other more of utility nodes in our graph, and we will take a look at how it's all connected together. So some utility nodes. Basically, we want to save some tokens. We want to increase the speed of our agent. And as you might have probably guessed, we don't need the full conversation history hanging there just after each step. So ideally, when we achieved a certain point, we clarified the user plan. We want to drop the whole conversation before and leave only the part that is interesting to us, the artifact, the user plan. And the same with the suggestion stage. We want to clear the history after like each suggestion stage is finished, and leave only the important artifact, the plan suggestion. Yeah, so to implement this, we also wrote some custom nodes. So what I'm doing here, if I represent this on the graph, basically I'm plugging some helper nodes here where the arrows are, and after each subgraph, I'm saving my artifact, the stuff that is interesting for me in the storage, and I'm summarizing, like compressing my history. And here we should probably take a look at this interesting part of the Koog framework, the storage thing. Again, it's coming from the agent context. You can access it here. And what it allows us to do, it allows us to like maintain a storage, a map, a concurrently safe map for each agent run, because it's normal that when building complex workflows, we don't want to pass all the data down the graph because it will grow and grow and grow and grow. So we want some more simple approach to the like state management. That's why you can use the storage functionality. And to use this, you basically need to define storage keys that are just some keys. They're always unique. You don't have to come up with a unique name. The name is just for you to debug it, to just understand the idea quickly. But every invocation of the create storage key is creating a unique key. And then you can use those keys to store some data and later to retrieve some data. And this is actually the recommended way to manage the state, to like temporarily persist some data for each agent run. And yeah, and I'm using it here to like preserve my artifacts and to be able like to clear the history, and so that I don't have to pass all those classes down the graph.
Yeah, like for those of you who are familiar already with the Cater framework, basically the design of the storage is taken from the Cater's HTTP pipeline attributes, whereas basically the idea of HTTP pipeline in the Cater framework and in general is very much similar to the way you write graphs. So basically you have some value that you transform to something new, and then you pass it up to the next stage, for example, to like sending HTTP request. And before sending HTTP request, you need to like serialize the data using some information from some of the plugins, for example, of Cater. And then eventually these straightforward paths don't always work as you desire, because like you need to pass some intermediate steps and then like reuse it in the future. And basically this storage idea, which is again similar to the attributes in Cater, is exactly that. So it's like a type safe map that allows you to like save something and then like load it and reuse in the future.
Yeah, exactly. And one more interesting thing that we're using here, again, there is a number of nice methods to work with history in Koog, and one of the most interesting probably is the replace history with TLDR extension method. And what it allows us to do, basically, it performs an additional request to the LLM with some preset prompt, asking to summarize the whole conversation history before this point to a single message containing only important parts. And so we can preserve the general idea and the state of the agent while cutting all the stuff that we don't need. And yeah, so that's why we're using it here. And again, it's used inside LLM write session because it would change the prompt, because it would drop all the messages that were here, except for system messages, of course, because system messages are special, and then replace all the messages with the LDR message.
Yeah. Would you maybe like to also explain a little bit about the strategy parameter and whether it's needed at all, because it doesn't probably make sense for
yeah, sure. Yeah, sure. So this is actually, in this case, the strategy parameter is not needed because this is the default strategy. But there's a number of strategies that we can use to manage how exactly it will be compressed. For example, we can decide that we don't want to compress the whole history. We only want to compress like each history compression chunked, like each 100 messages, or we want to compress only messages after a certain timestamp, or only like last n messages. And also there is like a more powerful concept that allows us to specify the exact concepts that we want to preserve in the resulting, like the LDR message. I guess we can just take a look at the KDoc here, and actually, as you can see, all the like strategies are specified here, and there is also like retrieve facts from history strategy, retrieve facts from history, and it takes a list of concepts. Concept. I have to import it. Yep. Import. Why it's not concept? Yeah. Sorry. Okay, because it's just complaining because I didn't specify the correct constructor parameters. Yeah. So basically, we can like specify a keyword for this concept, like for example, the state, and then the description, like the achieved state, the achieved like planning state so far. And then we also need to specify the fact type, which is just like a single fact. Yeah. So with this approach, we can control how the history will be compressed more precisely. So we can just guide the LLM to pay attention to certain parts if we want to highlight only like specific parts in the history.
Yeah, and also like basically you don't have to specify one concept, but basically it's a vararg argument. So you can specify as many concepts as you like. For example, in one of the agents that I know, we have like around like 20 of them, or like 15. And also like some concepts might have like a single fact type, which means that the LLM will like search through the whole history of what has been done and try to find out the answer on like a single question. For example, what is the achieved state? But also there is a multiple fact type, which is basically a list of facts. For example, I don't know, you can specify a concept which is the city, for example, and the description would be, for example, interesting city that the user wants to visit, and the fact type will be multiple. So the LLM, or even like some other model, like not the currently used one, will like try to search throughout the whole history and retrieve all the relevant facts not necessarily the city names, but the facts that the LLM decides that are like relevant to this concept. And there'll be like multiple of them. And then this strategy, the replace with TLDR with fact retrieval, what it will do, it will search everything and then reconstruct the conversation so that it naturally follows the conversational attitude. So like the user asks, what do you remember about like what were important like cities about the user that the user wants to like visit? And then there will be like an answer of the LLM with like a list of cities, and then like a question from the user. Okay, thanks. Now let's continue. I'm a little bit like oversimplifying the thing, but the idea is like that. And if you really want to learn more about that, please feel free to check the article that has been recently published on the JetBrains blog post channel by Denis Domansky, who is our machine learning engineer. So he has described a lot about like trying to make this history working perfectly, and he has like specified like all the mistakes that were made, and then like how he achieved that the strategy is working perfectly. So like there is a lot of prompt engineering out under the hood, and a lot of techniques that he had to use. So if you're interested, please feel free to check it out.
Yeah, I guess you're talking about this.
Exactly. It's like when tool calling becomes an addiction.
Yeah, anyways, it's a great read, so I definitely recommend you to check this out also. And let's get back to our strategy and just see how it all comes together, right?
Yeah, sure. So let's probably like revert the change of the history compression strategy.
Yeah, sure. Because here, like, we don't want to, it's more simple agent. We don't want to do some complicated history stuff. It's we're already saving the stuff that we want to use later in our storage, and that's why we can basically rewrite the whole history. Yeah, and let's check how this. Oh yeah, and another interesting part here is that we are also using a structured output. And why do we need the structured output here? Because when the user replies to the suggested plan, we want LLM to classify the reply. Did the user accept the plan, or did they reject the plan, and they're asking for some clarifications? So that's why we're using a structured output here, and it's actually quite easy to use. You just using the node LLM request structure here and passing a serializable Kotlin class that is marked with LLM description annotations to help the LLM to understand what exactly each field means. So for example, here I'm saying like, this is the user feedback to the plan suggestion, and that this is accepted property means that whether the plan suggestion is accepted or not. And the message should be just the original message from the user. So I'm utilizing the power of structured output to make my life easier and make the graphs nicer. Yeah, and to finally connect this all together, we're using edges DSL. And with edges DSL, when you're already familiar with this one, again, Vadim showed this on the previous live stream, but there's a bit more syntax sugar when the nodes are compatible without any transformations. So for example, as you can see here, like node start, it will produce user input, because that's what the strategy takes. And then the next node, the setup node, takes the same type. We don't need to do any transformations here. And we also don't have any specific conditions here, that because the strategy here, like in this part of our graph, it's sequential. And we can use then function to just define a sequential strategy, a sequential piece of the graph with compatible nodes. So we are connecting node start, the input of the strategy with the node setup. Then from the node setup that produces a string, we are going to clarify user plan stage. It's a subgraph that will use the tools provided to ask the user, check the dates, and provide us with the final user plan. Then we're going to the save user plan node to trim the history and save the artifact of the previous state of the previous stage, which is the trip plan. And then similar part, we're preparing an initial plan request, because at this point it will be the first time we're asking the agent to suggest a plan, then connecting this initial plan request with this suggest plan. Again, all the types are compatible. As you can see, this node, it produces suggest plan request, and this node takes this suggest plan request. And the same approach, we're saving the produced plan suggestion to our storage, and again trimming the history. But then there is a bit of conditional logic here, because we want to define this part when the agent has to decide. So we need to show the suggested plan, the first generated plan, to the user using this show plan suggestion node, which basically prints the plan to the user and asks for a feedback. And we're transforming it to string. We're using a string or default method here, because the plan is not the string. It's some class. It's a trip plan class, and we want to show a nicely formatted message to the user. That's why we're transforming it here and showing as a string. Then from show plan suggestion, we're going to the process user feedback node, which I just showed you. It's a structured output request. We're requesting the model to classify user message and provide us with a structure. And then we can use this provided structure to decide where to go next. So if the resulted structure is not if the model decided that the user feedback, the plan is not accepted, that the user provided feedback and is asking for correction, then we're taking the message, the user message, and going back here. So we're going back to this stage. We're creating a plan correction request. Otherwise, if the user decided that okay, this plan is fine, I'm taking it, we're just we're going to the node finish. So basically, we're going to the node finish, and we're taking the final generated plan from our storage. All those transformed and on condition methods, all those functions have access to the agent context, the same as the node. You can type this and see that there is an agent context here, so you can use the same properties, the same methods to interact with your agent. And so that's why I'm using storage get value in transformed here to extract the latest version of the plan, and I'm returning it. I'm passing it to my node finish to return it as a result of the agent execution. And this last part here, it's about if the user decided to ask for a correction, we're forwarding this to create correction request, and then going back to the suggest plan. So it's more complicated than the simple strategy, but that's exactly the point, because with custom strategies we can control the desired behavior of the agent. We can divide the execution flow to certain stages, to certain steps, and then we can combine, and then we can connect those steps with the logic that we want to have. And I guess we can run the agent to see that it actually works. and to see like how it performs. So I'm running it here, and yeah, so we should see the message, like the initial message from the agent. And I'm going to use some prepared prompt because I don't want to type it. But this prompt basically asks that, okay, I'm going like to Amsterdam in 2 weeks for 3 days, and I'm interested in culture, exploring interesting sites, and trying some local food. I'm going to run it, and we should see the output from the like event handler that I added for this agent here. That it actually calls some tools. It adds some dates because I mentioned here that I'm going in 2 weeks for 3 days, so it has to perform some maths to get the exact dates. And yeah, we should see here that the agent actually transitions to the next step, and it starts to call Google Maps tools to like perform some search functionality using Google Maps. And it should probably take like a bit more time, and I guess we can like answer some questions while the agent is running, if there's some questions here.
Yeah, actually there are some. So for example, one of the questions I actually marked for the later, but I think that's like actually very much relevant here. Is there a feature to visualize the network of execution automatically from the DSL? For example, plant UML, Mermaid, GraphViz, etc. So yes, we are basically working on two things. One of the things is an IDE plugin that will allow you to see all the traces of what's happening right now in the agent. And also it will draw the currently running agent, and it will highlight what node is being executed in a form of a graph similar to the one that Andrei has shown at his other desktop window. At the same time, we are also working, and basically it's going to be available in the nearest release, 040 of Koog. We are working on the lang fuse and 1DB support. So these are pretty popular tools for agent observability, and not only agent observability as well. And one of the features of Langfuse, for example, is being able to visualize and draw the agent graph. So these are things that will be available pretty soon. And right now, another funny thing that I learned from our developer advocate, Anton Arkhipov from the Kotlin team, is basically you can select the whole code of your agent graph, pass it over to AI assistant or to Juni, and ask like, please, can you draw the code for the mermaid diagram? And then it will dump you the format, and then you can use the IntelliJ Mermaid viewer or something like that to be able to like view the diagram. I've never thought about it this way, but basically it's possible, and it works. Not always reliable, but pretty great.
Yeah, and I just wanted to highlight something because, sorry, from the window. Yeah, as you can see, we got an error here, and the error basically says, yeah, let me bring this up. That is some tool arguments failed to parse. So basically, we specified a tool schema to the LLM, but the LLM returned a malformed tool arguments. And unfortunately, with the like current state of LLMs, it might still happen. So that's a good point to always verify your agent with different models, and also to like try and tweak some parameters. For example, while testing this trip planning agent, I got this error several times, and sometimes it happens, sometimes it doesn't happen. And for example, I can switch to like different model, GPT-4o in this case, and it should be more reliable. So this is something that you, I can provide the same prompt here.
Don't you want to switch the temperature as well?
You mean like turning it down a little bit?
Yeah.
Yeah, we can always like set it to 0.2. And yeah, let's just check. Let's just check how the OpenAI model will do. I see that it's running. It's searching some like places and stuff. So yeah, we should see the like after some time, because I prompted the agent. Basically, I played with the agent while developing it, of course, and I prompted, as you saw probably, the prompt for the suggest. Let me search for it. Yeah, the prompt for the suggest plan stage. It's quite long because by default I observed that the models didn't call Google Maps tools that much because they were lazy. They decided like, oh, all right, I just call like the search tool 1 or 2 times and that's fine. That's why I like decided to put some more requirements here, to put some more guidelines, to basically, yeah, like to guide the model to use more tools. And yeah, so that's why, as you can see, it's like calling more tools right now because yeah, it just decides to search for some historical landmarks and some local food. Yeah, so we should see some result. Yep, and we got it. So this is the first like plan suggestion from the agent, and it's printed out as a markdown because again I prompted the agent to provide me a response in the markdown format to be able to read it easily. And yeah, like here's some plan for day 1, for the day 2, some museums, some restaurants, and as a response I can type, for example, like that's fine. And yeah, the agent is finished because it classified this response as plan accepted. And yeah, and we got our final plan here, which is basically the same as what was printed before.
Yeah, Andrei, there is a like a related question. I wanted to ask that how can I automatically rely in that case the structure type error? So yeah, let me take that one. So basically, we have a few options in Koog. So one of them is the node request LLM structured. Andrei, could you please like scroll to that one?
Oh yeah, sure. Node LLM, yeah, request structure.
Yeah, so it has a few parameters, and basically Andrei is the person responsible for that awesome support in Koog. So it has a few optional parameters. So one of them is a list of examples that you can provide to the LLM so that it knows approximately what are the possible outputs. And another thing is, yeah, could you please scroll a little bit? Yeah, I see it. Yeah, another one is fixing parser, I guess, right? Could you please show us how it looks?
Yeah, sure.
Yeah, so basically one of the things is you can try a different model for specifically parsing the structured response. Another one is basically there is a number of retries, and you can try like 3 or 5 so that the model will retry again and again, and it will get the parsing error as the input, and it will try again with another attempt. And also like there are some other parameters that you can implement. And another thing that you can do is basically if the problem is happening, for example, in a subgraph or in some other node like tool node, what we also have in Koog is we have a retry node, which takes a condition, what has to be true, and then number of retries, and then any node or subgraph as a parameter. And you can wrap any workflow, any like node or subgraph inside of this retry component. That will work for you so that it will retry unless the condition is true. I don't remember the exact signature, but I guess
Yeah, I guess it's we can just say retry by subgraph with retry.
Yeah, exactly.
And you can
So
again like it's the same. It's kind of similar to subgraph with task, and you can check the definition. You can check the kdoc for the parameters that that you need to pass here and what this subgraph with try exactly does.
Yeah. So unless the condition about the output is true, it will retry anything that is wrapped in this subgraph. So that's the solution for the question that is being asked.
Yep. And I guess, yeah, I see that the agent is working. And yeah, just keep in mind that you always have to test the model that you're going to use, because if you roll out something with the model that you didn't test, it might behave differently, because like different models, different LLMs have their own strengths and weaknesses. So yeah, always test the workflow with the exact model that you're going to use in the production. Yep, and I guess we need to wrap up soon. So maybe we can answer one or two more questions.
Yeah, sure. I actually have marked like 7 questions, but we can just answer all of them very quickly. Yeah, the first 2 are like from the same person and they are related. So the like Hiro or Hero, sorry if I'm not pronouncing it correctly, is asking, I'm wondering how much to include in a single agent graph. Should preparing the unrelated to LLM be should pre-processing unrelated to LLM be performed outside of the agent? And the second part of this question is probably this one. Also, when simply processing LLM results and passing them to the next LLM, should I divide the agent or perform the processing within the single agent graph? So basically, these things we already touched. Regarding the second part, it very much depends on your use case. If you have completely independent parts and you don't need to pass any data or share the history between the steps or between the agents, then you don't have to write a custom graph. You can split into like independent agents. And also you can like split into like 2 agents and provide both as tools to a third agents. Koog also allows you to do that. But then if you want to like share the history throughout the conversation between the first one and the second one, basically what Andrei has been showing today, then you need to write a custom graph. Andrei, would you like to comment about the first part of this question?
Yeah, I'm wondering how much to include in a single agent graph. Yeah, I guess preprocessing can be, if it relates to the whole like agent logic, you can implement it as a node. For example, I put a setup node here as the first step, but you don't have to like interact with an LLM in this node. So I guess I would say it depends on how heavily this preprocessing logic is tied to the agent logic. If it's something that is relevant only to the agent, I would probably put it as like a custom node, as the first custom node in my graph. But if it's something like used in multiple places, then it's fine to process it out out of scope and then provide already some nice structured data as an input.
Yeah, I think that you don't have to like, there are no strict rules here. If it's like completely unrelated to the agent logic, then you can basically do the preparation in your own code and then provide it as a context to the agent. Another thing that maybe like we will touch in one of our further live streams or videos is persistency. So the graph structure, one of the core values of the graph structure is being able to save the history and save the whole state machine to a disk or to any other type of storage like S3, which can be like on your device or in the cloud, and then restore it from the same place where it stopped. So if you want this capability for your pre-processing logic, then it might make sense. Otherwise, you don't have to.
Yeah.
The next question is, I'm curious to see a React agent. The simple flows are very directed, fixed, rigid. Whereas with the React loop, the LLM can decide multiple rounds of tool calls in a loop, possibly even parallel call. Yes, that's correct. And we also have the React strategy out of the box in Koog. And you can also customize like how often do you like the LLM to give you the thought or like the reasoning step. And also under the hood in Koog framework, all tool calls can be parallel, and we actually receive a list of tool calls from the LLM. And even to the default or single run strategy, you can pass a parameter and change this behavior. So there are like a few parameters that regulate this behavior of the LLM, and we can accept multiple tool calls, and then multiple tool calls will be executed. That is actually, by the way, a very good pattern to save your money and time, because you don't have to request LLM multiple times for that. I hope that answers the question.
Yeah.
The next one is, I think I already mentioned it already, but I think it's kind of important, and I'll mention it twice. Thinking about the agentic memory, will there be possible support for on-device memory handling with object box or vector search capable? Specifically with the object box, we didn't have any plans to support that. But yes, Koog has two kind of related features. One of them is called exactly agent memory, which is designed to like retrieve specific facts from the history. And you can put this logic anywhere inside your graph, and then save these facts for the further executions of other agents or the same agent, but in the future, different like runs of this agent. You can save this data to any storage. A storage of the memory in Koog is basically an interface that anyone can implement. It has like 4 methods: create, read, update, and delete. Pretty straightforward. And then you can use vector database. You can store it on your local disk or in S3 or even in some on-device storage. And another thing is persistency. It's specifically this storing of not only the history of the agent, but also of the whole state machine of the agent, the whole graph. So this is more of a, for example, server-side feature. You can store the whole state machine on the disk after each step, so that when someone breaks and the server dies and it runs again on another machine, you can load the whole state machine, the whole graph, and the history and the state of the agent, including the storage and everything else. Of course, you have to make everything serializable for that. You restore it from the latest checkpoint, and then you continue from here, from the latest point of execution. So both features are available on any platform, on any device, and you can do it in mobile or even on the server side. And
Yeah.
the next question is actually related. So I can imagine deploying an agent with Spring REST and then deploying it with something like Kubernetes. Yes, that's very much correct use case, very much valid use case. And I would say that likely a lot of agents will be running on the server. And for sure, you can deploy your agents anywhere. And basically, as tools are any functions, that they can also invoke HTTP requests or MCP tools, like Andrei has been showing today. And also, we have a Spring Boot support out of the box. So you can make your beans a Koog tools and bind them to your agent. So that is also possible. And in the nearest release, we will also provide the Cater support for Koog.
Yeah, Vadim, sorry to interrupt you. I guess we're a bit short on time, so probably we can like ask if there's any questions left, we can answer them in the chat, in the Koog Agentic Framework chat in Kotlin Slack. Or again, you can always feel free to create new GitHub discussions or issues. Yep. And do you want to say something in the end?
Yeah, I think the last question is amazing for the end of this discussion. Feel free to go to our GitHub. It's github.com/jetbrains/Koog. Feel free to open our examples folder in this repository, and we are always open to any contributions, including examples or even features. So feel free to suggest any edits, and we'll be happy to discuss it.
Yeah, absolutely. Well, I guess bye-bye, everyone, and thank you for joining and for asking lots of questions. I hope I did my best to explain all the logic, all the different functionalities of the Koog framework. And yeah, if you have any questions, feel free to ask us in the Slack on the GitHub. And yeah, thank you, everyone.
Yeah, thank you, everyone, and see you in the next one.
Yep, bye-bye.